Welcome to this explainer by Forge College. Grab your tools because today we are heading straight to the engineer's workbench. Now, if you remember our previous lesson from the Bitcoin fundamentals track, specifically the transaction structure overview, we looked at the theoretical blueprints of how a Bitcoin transaction is shaped. Well, today we're actually building one. We're going to manually construct a raw transaction skeleton, literally byte by byte, putting every single piece in its exact right place. So let's dive right into this. Here is the blueprint drafting process for today's explainer. We're going to start with an intro to the workbench, gather up our UTXO parts, frame the skeleton foundation, wire the transaction inputs, route the outputs, and finally, wrap it up with assembly and validation.
All right, let's kick things off with Section 1, Intro to the Workbench, Drafting the Skeleton. So, our absolute main goal today is to assemble a raw structural draft using placeholders. And I want to be super clear here. We are not signing or broadcasting anything to the network just yet. This is just the skeleton. Now, the very first rule of handling our raw materials on this workbench involves how we actually read the data. As humans, we naturally read data from left to right, right? That's called big-endian format. But the Bitcoin network? It's a little different. It actually prefers to read many of its byte sequences flipped completely backwards in what's known as little-endian format. So when we move our strings onto the wire, we literally have to flip them. Hey, don't judge its quirks. Every machine has its own love language, and Bitcoin loves little-endian.
Moving right along to Section 2, Gathering the UTXO parts, which are essentially our raw materials.
So, before we start assembling, we need to gather our parts off the shelf. In the Bitcoin world, these are the unspent transaction outputs, or UTXOs. What exactly do we need to pull from these previous UTXOs? Well, we have four absolutely essential components. First, the massive 32-byte transaction ID, or txid. Second, the output index, commonly called the vout, which tells us exactly which output we're grabbing. Third is the value, measured in satoshis. And fourth, the scriptPubKey, which is the locking script. If you think about Forge College's hands-on approach to learning, these are the actual, real data points you must extract from the blockchain before you can even think about wiring up a new transaction draft.
Okay, with all our parts gathered and sitting right here on the workbench, let's look at Section 3, Framing the Skeleton Foundation.
Take a look at this master specification chart. Notice that every single piece of a transaction has a very precise wire position. It's like a highly organized assembly line. It flows sequentially. We start with a version number, followed by the input count, and then the inputs themselves. Next comes the output count, the outputs, and finally the lock time. The signers who are eventually going to validate this transaction, they expect every single byte block to be in this exact predictable sequence. If it's out of order, even slightly, the machine simply won't start.
So let's break that down into physical assembly steps. Step 1, we basically bolt down the version number. This is typically version 1, which we write as 4 bytes in that little-endian format we talked about. 0, 1, followed by 6 zeros. Step 2 is writing the input count. Step 3 is serializing the inputs, and so on, right down the line to appending the lock time in Step 6. It's incredibly logical, but let's see how this builds when we hit a very special kind of counter back in Step 2.
That counter is called a varint, short for variable length integer. You can kind of think of a varint like a dynamic shipping label because, a transaction could have one single input or it could have 1,000 inputs. We need a flexible way to tell the network what's coming next. The varint simply tells the assembly line, hey, exactly this many parts are inside the upcoming box. It's brilliant because it saves a ton of space and keeps the processing highly efficient.
All right, chassis framed. We're now ready for Section 4, Wiring the Transaction Inputs.
32. Now, that might not sound like a lot in everyday life, but in byte terms, it's a massive number. The transaction ID, or txid, that identifies exactly where our power is coming from is exactly 32 bytes long. And remember our little-endian rule from a few minutes ago. This entire 32-byte string, which you'd normally read from left to right, must be completely flipped backwards to fit perfectly into the machine's receptors on the wire.
So, let's walk through the precise sequential wiring of an input. First up, that flipped 32-byte txid. Second, the 4-byte index, which points to the exact output we're spending. Third, our handy varint telling the machine the length of the upcoming script. Fourth, and honestly, this is absolutely vital for today's lesson, a temporary placeholder scriptPubKey. Since we're just building a skeleton draft right now, we don't have the real cryptographic signature yet, so we just use a tiny marker, like a zero-length push, just to hold the space. And finally, we cap off the input with a 4-byte sequence number.
Awesome! Power is officially wired in.
Now, let's move to Section 5, routing the transaction outputs to tell that power where to go.
8 bytes. When we record the payment amount, the actual output value in satoshis, it requires exactly 8 bytes of space, once again, in little-endian format. And here's what's cool. Whether you're sending one single, lonely satoshi or a million satoshis, the machine always allocates exactly 8 bytes to securely and uniformly record that exact amount.
Let's look at the final output wiring. You'll notice it's actually a bit simpler than the input. We start with that 8-byte value representing our satoshis, then a varint telling us the script length, and finally, the scriptPubKey. This scriptPubKey is the locking script. We are quite literally taking the satoshis and snapping a complex mathematical padlock right onto them, which dictates exactly what conditions must be met for someone to spend them next.
We are almost there, folks. Let's head into our final section, final assembly and validation.
The very final piece of our structural puzzle is the lock time. This gets snapped into place at the absolute end of our transaction hex string. For a standard transaction that's meant to be valid immediately, this is just 4 bytes of zeros. 000000000.
And here is the beautiful result of our workbench session. We've produced a perfectly structured, serialized hex string draft. It is completely ready for a signer program to step in and consume. And alongside it, we usually generate a human-readable JSON map so we can easily review the work we just did.
But wait, before we declare a total victory, we have to ask a crucial question. Does this draft parse back to match what we initially expected? As an engineer, your final QA check is to take that long hex string you just built and parse it locally. You count the fields, check the byte lengths, and ensure everything perfectly matches those raw UTXO materials we gathered off the shelf at the very beginning. If it parses perfectly, your foundation is rock solid. I want to leave you with this final thought. Correct assembly is the essential step before signing. Precise, manual byte assembly is the true foundation of Bitcoin engineering. I mean, you can't cryptographically sign a disorganized mess of bytes, right? But it does beg the question, what happens if even a single microscopic byte is out of place when the signers step in? If you found this deep dive into the transaction machine fascinating and want to discover exactly how we lock these bytes down, I highly recommend visiting forge.college to explore more in-depth courses. Thanks for joining me on this explainer, and keep building.